Okay, ladies, as we move into chapter 3, we are going to be looking at bivariate data. So far this year, all the data sets that we have been describing using SOCs, graphing, has been univariate data, but now we're going to be looking at bivariate data. So prefix bi obviously means two, and so we're going to be looking at two sets of data and examining the relationship between those two sets of data. Okay, so far we've just done univariate data where we've looked at one variable at a time. Now we're going to be looking at bivariate data with two variables, and we're looking at the nature of the relationship, looking to see if one variable explains or causes changes in the other. And so you've probably been familiar with the term independent and dependent variable from science classes, but in statistics, we're going to define the variables as the response variable or the explanatory variable. The response variable measures the outcome, and in science and other applications, that's the dependent variable, which gets plotted on the y-axis. But in statistics, we're going to refer to it as the response variable. And the explanatory variable is then your independent variable, which is plotted on the x-axis. And it's the variable that helps explain or influence the changes in the response variable. You'll want to be familiar with the vocabulary of response variable and explanatory variable as we move forward and look at bivariate data. Let me give you some common examples, or not common, but some examples of bivariate data. So one example could be shoe size and height, and we will actually collect data and look at the relationship between the two, but you might think that there's a relationship between how big someone's foot is and how tall they are. Another example could be SAT math and verbal scores. Are there a relationship between how you do on the math section and how you do on the verbal? A couple more: amount of alcohol consumed and body temperature. Amount of time studying hopefully indicates or leads to a higher test score. Here's the tricky part. Just because we call one variable explanatory and the other response, if we see a relationship between those two variables, it doesn't mean that one causes changes in the other. So you really want to avoid using the word cause, okay? And there's a phrase that you'll probably hear me use over and over again in this unit, and that is correlation does not imply causation. Just because two variables are related to one another doesn't mean that one causes changes in the other. And we'll get into some examples and talk about correlation a little bit more in this lesson. Just like with univariate data, when we're working with bivariate data, we want to look at the data graphically, and we also want to look at the data numerically. So the scatter plot is going to be the type of graph that we use to graph bivariate data, okay? Both pieces of data have to be quantitative or numeric in order to plot on a scatter plot. If one of the variables is categorical or qualitative, then a scatter plot is not going to be a good option for your data. So both variables have to be quantitative. Once you decide which variable is explanatory and which one's response, and sometimes they can be interchangeable. If you go back to the example of shoe size and height, okay, I venture to say shoe size would do a pretty good job of explaining height, but you could probably switch or reverse the two and say height would probably do a pretty good job of explaining shoe size. That's not always the case where they're interchangeable, so you really have to think about the variables, okay? Obviously, an explanatory variable is going to go on the x-axis of your scatter plot, and the response variable is going to go on the y-axis. Once you graph your ordered pairs, You want to look for any patterns or deviations from the pattern. And then just like with univariate data, we described SOCs. For bivariate data, you want to comment on the form, the direction, and the strength. Okay. And then last but not least, if there are any outliers or influential observations, and a little bit later in the unit, we will spend some time talking about the difference between the two, but you'd want to definitely comment on any outliers. So what do I mean by form, direction, and strength? If we take a look at this example, okay, our explanatory variable is number of beers consumed, and the response is blood alcohol content. So obviously, the more beers a person would consume, the higher the blood alcohol content. So direction, form, and strength. So for form, the best way to describe it would be to look to see if the data is linear or nonlinear. If it's nonlinear and you can describe what type of function the points in the scatter plot are modeling, then you could feel free to say, instead of nonlinear, you could say exponential or logistic for logarithmic, okay? But if you're not sure, then just play it safe and say it's nonlinear. So if you look at the form of these points, they fall pretty close to a line, and probably back in Algebra 1, maybe Algebra 2, maybe even pre-algebra, you called this a best fit line. Okay, so if you kind of imagine a line going through the middle of the points, touching as many points as possible, would that, line, or would it be a curve? So form is really whether the points form a linear function or a non-linear function, okay? For strength, okay, that's basically how tight the points are to the best fit line, okay? So words like weak, moderate, strong. And then if you kind of can't decide if it's weak or moderate, then you can always say the relationship is weak to moderate or moderate to strong. And so for this one, the points are all pretty close to the line, and I would classify the strength for this data to be moderate to strong. And then last but not least, we have direction. Okay, so obviously your choices for direction are either positive or negative. Okay, this graph, and you can look at the slope of your best fit line. So the direction of this graph is positive. And once you say whether it's positive or negative, you need to elaborate on that and say, as number of beers increases, blood alcohol content increases as well. If the relationship were negative, obviously, as whatever's on the x-axis, as your explanatory variable increases, your response variable decreases. And I think I have an example of a negative association coming up. Here's an example of some data that I collected with my class last year. Okay, so I'm going to kind of eyeball and draw in what I feel would be a decent best fit line. So the direction for this data is obviously positive. Okay, as height increases, shoe size tends to increase. Okay, I would say the form is somewhat linear, or linear would be fine. There's no curved pattern to the data. And then what am I missing? Direction, form, strength. And I would say that this, again, is kind of moderate. And in terms of weak, moderate, strong, we're going to talk about a statistic that helps us classify the strength of the relationship a little bit better in a minute. Next example, this obviously is pretty linear. So as the number of classes a student misses, we're looking at their exam score. So for this one, I would say the form is pretty linear. The direction is obviously negative. So as number of missed classes increases, exam score tends to decrease, okay? Form, I would say this is very definitely linear. And then strength, I would say this relationship's pretty strong because as you look at where I penciled in that best fit line, the points are clustered pretty tight to the line. Versus if we go back to the last example, there's a little more scatter or distance between the points and the best fit line, okay? All right, so I said a minute ago that we were going to look at a statistic that helps us determine the strength of a linear relationship, and that statistic is called the correlation coefficient, and we use the letter R to describe the correlation of the data set. It measures the strength and the direction of the linear relationship between two quantitative variables. You have to have quantitative data or numeric data, okay? In the box, or what I'm about to box, is the formula for the correlation coefficient. And there are a couple different types of correlation. There's Spearman, there's Pearson's. I believe what we're going to use in this class is Pearson's correlation coefficient, and you'll hear a little bit more about it in the second video that you're going to watch. If R is positive, then obviously there's a positive relationship or association between your explanatory and response variable. If R is negative, then there's a negative association between the two variables. R is always going to be between 1 and -1. Okay, if you ever get an R value of 2.2, something is wrong. Okay, so be cognizant of the fact that R will always be between 1 and -1. Okay. Last thing we're going to talk about today in this podcast is not that. Moving ahead here. Correlation. It is not resistant. So outliers can strongly affect the value of R. Okay. Keep in mind that R only measures the strength of a linear relationship. If your relationship isn't linear, then don't even interpret the value of R. Last but not least, it measures the extent of the association, but it does not apply cause and effect. So just because two variables have a high correlation does not mean that the explanatory variable causes the effect in the response variable. And then you'll see some of this in the other video that you're going to watch, but correlation values between about 0.5 and -0.5 typically indicate a weak strength in the relationship. 0.5 to 0.8, pretty moderate, and then 0.8 to 1, strong. Okay, and then same thing over here, moderate and strong. It really just depends on your expectation. If you think there's no relationship between two variables, that means your correlation is going to be somewhere around 0. And you end up getting an R value of 0.33, that's probably a lot stronger than what you would have thought if you expected no relationship between the variables. So it somewhat depends on the context of the problem. Okay. Here's a couple examples of different correlations. So obviously correlation of 0 means there's no relationship between the two variables. And so you can take a look at these, and there are a couple more in the second podcast. So use that second link to learn a little bit more about correlation. And then at our next meeting, we will learn and talk about the formula for correlation and how to calculate correlation by hand and also on your calculator. Thanks for listening and tuning in, girls.